Hello Year 11s and welcome back to mathematics. In today's video, what we're going to be looking at is solving absolute value equations. Now, absolute value equations are equations where we involve the absolute value function that we looked at in the last lesson. So if you haven't looked at the last set of videos where we talk about what the absolute value function is, please go back and have a look at those videos first before coming to here. But what I'm going to do at the start here is just go through a quick recap of what the absolute value function does. Now, the absolute value is just these two lines that we see here where we put around a number or per numeral. What it tells me is that I take the magnitude or the size of the number and ignore the sign of the number. So for example, if I take the number 100 and I put it in the absolute value function, what's going to plop out is 100 because that is the magnitude or size of that number. 100 has just a size of 100. But if I also take negative 100 and put it inside my absolute values, well, the size of that number is just 100 and I ignore the negative sign. So here, the absolute value of negative 100 is 100 as well. And what I have on the screen and the top here is just a definition, that definition that we wrote in the last lesson, the algebraic definition of what the absolute value function is. The absolute value function, if the number is positive, which is what this first line tells me, so if the number is a positive number, if the number I'm putting into my absolute value function is a positive number, I'm just going to get back my original number, which is just x, which is what we had on this top example here. Whenever I chucked in a positive number like 100, I get back my original number. The second line, with second condition for my absolute value function, is what happens if I chuck in a negative number. So if I chuck in a negative number into my absolute value functions, what I get is the negative version of that original number. So here, I chucked in negative 100 into my absolute value function, and I got back 100. When you take a negative of a negative number, you just get back the positive version of that number, which is essentially what the absolute value function does. What we're doing in this section is looking at what happens when we solve equations that include these absolute value functions in it. Now here in your notes and also on here on the screen is a few sets of notes, and it's also in the booklet that you've probably downloaded or are getting a physical copy of. But when we're solving absolute value equations, there's three conditions that we're looking at. So here the sort of equation that we're looking at is of this form. Absolute value of ax plus b is equal to a number k. So last lesson we looked at graphing these types of graphs. So absolute value of ax plus b, that's just a general form of an absolute value function. A and b are just different values that we can substitute into our equation. And there's three things that can happen when you are solving this type of equation. And it all depends on the value of this k over here. So let's have a look. The first condition is if k is negative or if k is less than 0, the equation has no solutions. Okay, cool. So if k is less than 0, we have no solutions to our equations. There's no x values that satisfies this equation. If k is equal to 0, then there's one solution, and this is found by solving ax plus b is equal to 0. So if k is equal to 0, we've got one solution. And if k is greater than 0, there's two solutions, and we find them by solving these two equations. Ax plus b is equal to k, and ax plus b is equal to minus k. Now, why is that? Now, I've drawn an example of an absolute value function, and if you remember from last lesson, we looked at graphing absolute value functions, and we got this shape, which kind of looks like a V. Now, my V is made up of two linear functions. If you remember, we had two branches of my absolute value function. There's this side over here on the right, which is my positive version, so this is y is equal to ax plus b. And on the left-hand side, we've got the negative version. These two linear functions, y is equal to negative ax, and because I would put a bracket around it, it would be ax minus b for this one here. Okay, so we've got these two linear functions here that make up my absolute value function. But just to get an idea why these three conditions happen when we have different values of k, let's just draw up what would happen. If you remember from points of intersection, when we're trying to find the solution to one of these, we look at how many points of intersection that they are. So let's look at the first example. If k is less than 0, we're looking for a line which represents y is equal to a number that's less than 0. So let's draw it on the graph. So here, this is an example of a line where k is less than 0. We're looking for y values which are less than 0. So here, any number that's between this x-axis all the way down to negative infinity, that all works. Now, if you have a look at this purple line and my absolute value function, do they intersect and do they touch? Well, no, they don't intersect at all. which means that we have no solutions or no points where, no values of x where these two functions are going to exist at the same time. So here, this is why for the first condition, if k is less than 0, the equation has no solution. So here this is no solutions. Okay, let's have a look at the next condition. If k is equal to 0, now which line represents y is equal to 0? If you remember, the line that represents y is equal to 0 is just my x-axis along here. So this is my k is equal to 0. And now if you have a look at this line here and my absolute value function, where do these two graphs intersect? Well, there's one point on both graphs where they touch, and it's right on the vertex there. And so here, we're only going to have one solution. So here, when we have k equal to 0, we have one solution, which is exactly where ax plus b is equal to 0. So that's why we have the second condition. Let me try to write that again a little bit nicer. Here, so if k is equal to 0, we've got one solution. The final thing is when k is greater than 0. So where does y is greater than or equal to 0? So y is greater than 0 when we have a line somewhere up here, for example. So this is k is greater than 0. And if you have a look, how many times does it touch my absolute value function? It touches it twice. It touches it once, and this is on the green side, and it touches it once on the blue side. So it touches our graph twice because of those two branches of my absolute value function. So here we're going to have two solutions. And so the reason why we're solving these two equations here is because we're solving for ax plus b is equal to 0, which is my light blue line. So here, actually, let me try that right there again. So we're solving for two bits. We're solving for ax plus b, which is that light blue branch. And that's equal to k. But we're also solving for negative ax minus b is equal to k as well. So here, we're solving for these two equations. Now you have a look at what's written on those two equations. One of them is just, they both have ax plus b, and one of them is ax plus b is equal to negative k. Now if you notice, the one on the right, I can just multiply both sides by minus 1, and instead of having negative ax plus b, I'll have ax minus b. I'll have ax plus b is equal to minus k. And so that's why when we're solving absolute value equations, if the number that we're solving it with is greater than 0, we're going to have two solutions. We're going to have two solutions. Okay, so this is what happens when we solve absolute value equations. What I'm going to do is I'm going to go through a few examples where we solve this. And we're going to do it two ways. We're going to solve it first algebraically, where we use algebra and just apply this method that we see here. And then we're also going to look at it graphically, so looking at the coordinates and looking at the x values of those coordinates to see where these two graphs touch.